Yep. All right, here we go. Going back to integration by parts. So hopefully you watched the first couple of videos. We learned that if we have the integral of u dv, that is equal to uv minus the integral of v du, right? That's the integration by parts formula. And it was derived, believe it or not, from the product rule for differentiation. All right. Now, last time we looked at integrands of the form polynomial times exponential function. And when we had that, we saw that we wanted to let u be the polynomial piece, right? It seemed to work out for us. So you might be thinking, do I always let u equal the polynomial piece? Well, let's find that out. So let's look at something different today. Let's look at a polynomial times a logarithmic function to decide what should we let u equal. All right, so for example, let's do the integral of 3x ln of x dx, right? So let's pretend like we don't really know any better and we're thinking you always let u equal the first part, right? So all right, let's go about it that way. So I'm going to let u equal 3x. Now remember, when you decide what your u is, your dv is picked for you because it's got to be the rest. So dv would then have to be ln of x dx. So now you immediately compute du. That's just the derivative of u, which would be 3, and then times dx, right? Where there's a du, you need a dx. Just like when there's a dv, you need a dx. And then we're going to figure out what v is. Now, v is the antiderivative or the integral of ln of x. So you may not have that memorized, or you may have it memorized, but I'll hook you up. The integral of ln of x is x ln x minus x, all right? Remember, we don't need the plus c here because it's going to be taken care of in this integral there. So, okay, let's use the parts formula, right? Because think about it. You just represented this as the integral of u dv. So if that's the case, that means this is equal to uv minus the integral of v du, right? That's a valid formula. So, okay, so u times v, that would be 3x times x ln x minus x minus the integral of v du. I would pull the 3 out because it's a constant, I can. And then I get x ln x minus x dx. And the way this parts thing works is when you apply the formula, you look at this new integral that you get and you make a decision. Did it get better? All right. And the answer is it didn't get better. And arguably it got worse because you still have a product of a degree 1 polynomial times the log, but then you also have a difference here. So not that the difference is difficult to handle, but this certainly didn't get better. We can all agree to that. So since it didn't get better, it means it might not have been the way to pick. So in other words, letting u equal the polynomial might not have been the best way to go about doing this problem. All right, so I'm going to say cross that out and let me give this another go. All right, so let me actually redo this guy, and I'll actually rewrite it. The integral of 3x ln of x dx. Let me try letting u equal the log part. So let u equal ln of x. So then dv, now it's picked for me, right? You got to pick everything. So if u is ln of x, then dv's got to be the rest. So that's the 3x and the dx, right? Again, the dv goes with the dx. Du is the derivative of ln of x. That we know. That's 1 over x. And then, of course, dx because differential. And then v would be the integral of this, which 3 times a half x squared. That's going to be 3 halves x squared. Remember, to go from dv to v, you're integrating. To go from u to du, you're taking the derivative, right? So once again, though, you represented this as the integral of, that's my u, and then the rest of the stuff here was my dv. And so, again, we know that the integral of u dv is equal to uv minus the integral of v du. That's the integration by parts formula. So then I can write u times v. So I would rearrange that as 3 halves x squared ln of x minus the integral of v du. So I'd pull the 3 halves out. You can't pull the 1 over x out. You can only pull constants out. So v du is basically x squared times 1 over x dx, which maybe at first glance you're like, oh my God, I have a product. That's not a good thing, but it's really not a bad thing because you can simplify that product, right? Right? X squared times 1 over x, that's just x, right? We can simplify that however you want to think about it, right? X divides into that once and divides into one of those factors there. So I'm going to end up getting here, when I do this, 3 halves x squared ln x minus, and I'll take my time here for video flavor, 3/2 integral of x dx. So should be pretty clear that this is a much nicer integral than the one you started with. You can integrate x, okay? So if I do that, I'm going to get 3/2 x squared ln x. And again, for video flavor, I'll write 3/2 times. Now the integral of x is going to be 1/2 x squared. And then I can add my constant of integration. All right. And I don't need to have that plus c in parentheses here because of that 3/2, just because a constant's a constant. So c and negative 3/2 c is the same thing. It's just cleaner to look at it that way. All right. And then just one final spruceage here. 3/2 x squared ln of x, and then minus 3/4. All right. I don't know why I felt the need to put that in a different color, but I'm going to. All right. 3/4 x squared plus c. And there you have it. Okay, done. So you found a family of functions differing by a constant such that if you took the derivative of this, which by the way, you'd have to use the product rule on that first part there. If you took the derivative of that and you simplified it, you would get something that just simplified down to 3x ln of x. Okay? So a lot of good things happen here. I think noteworthy things, because think about it, and I'll just kind of review, right? When we had a polynomial times an exponential, then the move was let u equal the polynomial when we were doing integration by parts. If everything else you learned to that point failed, you had to use integration by parts, then you're going to let u equal the polynomial. Okay. Now we just looked at polynomial times log. And again, everything you've learned to this point, if you exhausted all those different possibilities, the standard u sub, all that stuff didn't work. Well, now it looks like if you're going to use parts, that let u equal the log part. All right. So the moral of the story is you have to decide. So if you have an integral and it's a product and you don't recognize a function whose derivative is, or a normal u substitution is not going to work, or anything else that you have learned, any sort of simplification is not going to work, and you decide to use integration by parts, right? That's another tool in the toolbox. Then you're going to pick a u and a dv and you're going to see if it works. How do you know if it works? Because once you apply the formula, you look at your integral. If your integral got better, then you know it worked. All right. If it got worse, it didn't work. If it's the same in difficulty level, then that actually could be a good thing. And we'll get to that in another video down the road. All right. So final problem that I want to look at here is, well, what do you think you do if you have polynomial times trig? Okay, what do you let u equal? So for example, if I had the integral of 5x times the sine of, say, 2x, what's going to work here? All right, so your options are this is what we'll do. We'll do this. We'll say option 1, let u equal 5x and let dv equal sine of 2x dx. That's option 1, and then do the problem, okay? Option 2 would be let u equal the trig piece, so let u equal sine of 2x, and then let dv equal the rest, which would be 5x dx, all right? So which one is it? Is this option going to work, or is that option going to work? Well, that's your homework, all right? So give it a shot. So do this problem, all right? Complete it, take a picture of it, and submit it into your Google Drive, and then we're good to go. Okay? Hope everyone's good. Stay safe. Be good. And we will do this again next week. Take care.